You clicked because you heard about a new chip technology that breaks the rules of physics. You are right to be skeptical because the current path to faster processors is hitting a hard wall. Traditional lithography cannot etch features smaller than a few nanometers without running into quantum uncertainty and massive energy costs. By the end of this, you will understand how engineers are bypassing these limits entirely by shifting from carving matter to growing it, turning the bottleneck for manufacturing into materials science. For decades, the story of computing has been a story of subtraction. We take a block of silicon and we carve away everything we do not need. This is top-down lithography. We shine light through masks, etch patterns, and repeat. It works, but it is hitting a physical ceiling. As we try to pack more transistors onto a chip, the features become so small that quantum effects start to interfere with the flow of electricity. The energy required to maintain these tiny structures is skyrocketing. We are trying to force order onto a material that wants to be chaotic. Here is the thing that changes everything. What if we stopped carving and started growing? Recent breakthroughs in mesoscale atomic engineering suggest we can create complex hardware architectures by manipulating matter at the atomic level, rather than etching it from the top down. This is not a minor improvement. It is a fundamental shift in how we build the foundation of our digital world. Instead of using a machine to cut away material, we're designing the conditions under which atoms arrange themselves into the shapes we need. Consider the material FePd2Te2, an anisotropic layered ferromagnet. In this substance, researchers have discovered that by manipulating hierarchical twin domains, they can induce specific magnetic states without any physical etching. These domains exist across multiple scales, from the atomic to the mesoscale. The result is a material with in-plane anisotropy and multi-scale order that behaves in ways traditional silicon never could. This is the pathway to AI hardware with intrinsic spintronic capabilities. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. To understand how this works, you need to look at the tools we use to predict it. Phase-Field Crystal modeling, often abbreviated as PFC, allows us to simulate dislocation dynamics and elastic deformations in thin crystalline sheets. These simulations reveal how defects form and how they can be managed. When we apply amplitude PFC modeling, we can identify specific local structural features that drive the spontaneous emergence of complex lattices. This means we can design materials with optimized charge transport properties before we ever synthesize a single gram of them. The implications for energy storage are equally profound. In traditional batteries, we rely on trial and error to find materials that can store and release ions efficiently. This is slow and expensive. With mesoscale engineering, we can engineer the thermodynamic control of self-assembly. We define the interparticle potentials, and the material organizes itself into high-coordination lattices that are inherently defect-tolerant. This allows for the creation of complex, three-dimensional lattice architectures that emerge spontaneously from simple particle interactions. This approach relies heavily on unsupervised machine learning applied to crystal growth simulations. The algorithms identify patterns that humans might miss, revealing how geometric frustration and local undercoordination in liquid phases affect the final lattice integrity. This data-driven method offers a way to engineer materials with specific magnetic states and charge transport properties that are impossible to achieve with conventional manufacturing. However, the transition from this theoretical potential to industrial reality is where the story gets complicated. While the ability to shift the bottleneck from fabrication to materials science is clear, we face significant hurdles. Current methods rely heavily on computationally intensive simulations. We can model these structures, but simulating the dynamics of defects across a large area takes immense computing power. Furthermore, the self-assembly of identical particles is not yet a high-throughput process. We can create beautiful hierarchical structures in a lab, but doing so deterministically at scale is a different challenge entirely. Practitioners in the field note that while soft matter crystallography offers tunability, it currently lags behind hard matter in structural diversity and stability. The emergence of geometrically frustrated growth complicates the prediction of final lattice integrity. We are dealing with systems where local undercoordination in liquid phases can lead to unpredictable outcomes. The primary knowledge gap lies in bridging the gap between simulated defect dynamics and scalable, defect-tolerant manufacturing processes. We need to move from observing these phenomena in controlled environments to controlling them in a factory setting. The transition from laboratory-scale discovery to industrial-grade deployment remains unproven. We have the theoretical framework and we have the simulation tools, but we lack the deterministic control required for mass production. This brings us to the core architectural shift. Mesoscale atomic engineering requires us to replace manufacturing processes with precise control of interparticle potentials. In the old paradigm, the primary lever for performance was geometric precision in fabrication. We made the shapes smaller and smaller. In this new paradigm, materials science and thermodynamic simulation become the primary levers for performance. We are no longer just building machines, we are programming the physics of the material itself. The potential is staggering. We are looking at a future where AI hardware is not limited by the scaling limits of conventional CMOS logic. We could see batteries that store energy more efficiently because their internal structure is optimized at the atomic level. We could see sensors and processors that are inherently more stable because they are designed to tolerate the defects that would destroy a traditional chip. But this future depends on solving the scaling problem. We need to figure out how to grow these hierarchical structures reliably, quickly, and cheaply. We need to understand how to control the self-assembly process so that it is not just a laboratory curiosity, but a viable industrial method. The shift from carving to growing is not just a change in technique, it is a change in philosophy. It is a recognition that the complexity we need to solve our problems is not something we can force from the outside, but something we can invite from the inside. The bottleneck has moved. It is no longer about how small we can etch. It is about how well we can understand and control the thermodynamics of self-assembly. This is the next frontier of engineering, and it is waiting for us to cross the threshold from simulation to scale. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.